So, friends, welcome to this lecture series of geomorphology, and we will talk about this mechanical weathering in this class. So, if you remember the last class, we are talking something about the prominent regions for mechanical weathering. What does it mean? And this mechanical weathering, the sitting joints or this pressure unloading was the prominent cause for this sitting joint development and hill slope evolution. So, in this class we will elaborate what is this sitting joints and how they are developed in the hilly terrains, in hills and valleys, how these sitting joints look alike and so on. So, if you see here the mountain terrains, we have valleys and hills, and we know the sitting joints they occur near to the surface and parallel to the topography and expands upward, the rock surface that expands upward. So, now you see here there is an example of the glaciated hilly terrains. Here we have valley and here we have hill. So, in hill and valley what we are getting here, the at valleys these sitting joints they are concave upward. However, in the hills that is convex upward. So, the topography of this hilly terrain like this, hills and valleys, hills and valley. Similarly, the sitting joints also follows this topographic profile and occurs like convex upward and concave upward, again convex upward. So, that means I want to say the sitting joints always follow the topographic profile locally. But if you consider yourself at this valley and the hill boundary, here the sitting joints they mix with each other, they intersect with each other. So, that is why now see one fracture is moving downward, another fracture moving upward. So, at this valley and hill junction they will intersect. So, once they intersect, two fractures they intersect. So, that means they will make the rock more fragile. So, at this hill and this valley boundary, the rocks are more prone to mechanical weathering due to these intersections of these sitting joints. Now, there is another example of pressure unloading is during tunneling. So, if you see rock always wants to expand toward the free space, because we know this sitting at the case of sitting joints the rock always expands upward, because upward is the atmosphere, it is the free, it is the pressure unloading, the overburden is less or the removal of the overburden. So, the rock will try to expand upward. Similarly, suppose we are making a tunnel here, suppose we are making a tunnel, that means we are creating artificial free space within the rock body. So, once we are creating artificial free spaces, the rocks of the surrounding they will try to expand downward, they will try to expand towards this free space. So, that is why the rock due to rock expansion, whatever this diameter of the tunnel we decide in earlier times or in during planning, whatever this diameter of the tunnel we decide, due to expansion of these rocks to this free space, its diameter gradually decreases. So, that is why during planning for this tunnel excavation, we have to take into consideration this factor also. To prevent the rocks to expand toward the tunnel space, sometimes we use these iron bars. So, iron bars are intact with the system and finally, it prevents further expansion. But in the initial time if we excavate some part of this tunnel and this as soon as we excavate we support by iron bars, then it is also difficult to handle the situation. So, that is why during tunneling we do phase wise. First phase of tunneling, first phase of the rock excavation occurs, we allow the rock to expand. So, once we allow the rock to expand, some of this rock body that will expand within the system. So, again we start digging one and then again we start tunneling. So, by further removal of the rock, then again we allow to expand. So, during subsequent excavation and stopping of the excavation, the rock will allow to expand within this tunneling system, and further we remove this rock and finally we support it by iron bars. That is why during tunneling this work does not go in a straight. It will first will expand, will allow the rock to expand sometimes, then we remove this excess material, then again we will work for this tunneling. So, like this phase wise we do this work. So, another type of rock expansion is called anticlinal valley and synclinal hill. So, what does it mean? Anticlinal valley and synclinal hill. Anticlinal valley and synclinal hill is formed in mature topography. Mature topography means topography. What is mature topography? That means structurally it has already reached to the optimum time, optimum size. So, that means what does it mean? If you see here, in a valley with small anticlines in Northampton, England, here the brittle sandstone beds break apart due to anticlinal valley and underlying the claystone bulged upward. So, now you see claystone, clay once it is reacts with water, we add water in the clay, it will expand. So, once it expands, that means in the tunneling, if we go back, remember this few minutes back we are talking something about tunneling. During tunneling we have to encounter different types of rocks. So, all those rocks do not behave similarly to the expansion coefficients. So, that is why those areas which are during tunneling which is encountered by granite, that will expand differently. If it is clay bed, that will expand differently, it is limestone, that will expand differently. So, the degree of expansion, that will depends upon the rock properties. Now, here we see in a valley or in an anticline we have sandstone body which is on the top, below is the claystone. We remove the sandstone part. Once we are removing the sandstone part, the clay will interact with the atmosphere and will absorb water vapor, it will try to expand. So, once it try to expand, here at the anticlinal part, once the removal of sandstone occurs, the clay will expand, it is bulging out. So, this is another example of a rock expansion. But anticlinal valley and synclinal ridge, that is a different issue, we will discuss here. What is anticlinal valley? Anticline, if you see, anticline means two sides of a limb or two limbs, they are dipping away from each other. Syncline, two limbs of a fold dipping towards each other. So, in anticline, the rock is under tremendous stress. We are extending the system, we are expanding the system, yet it is stretched, the rock is stretched. But in syncline, the rock are compressed, So, once the system is extended, it is stretching, so there will be cracks developed. Once those cracks are developed, through these cracks physical weathering, mechanical weathering occurs, removal of the material occurs. For example, if you see here in this figure given, it is an example from the Chitradurga schist belt, and it is there is a presently a reservoir is existing, that is called Bani Vilas Sagar. Now, you see here, earlier the granite was there at the basement. On the granite we have sandstone, clay stones, like here whatever is given, sandstone, conglomerate, dolomite, banded iron formation, phyllite, these are the constituent rocks. Now, if you see here, this granitic basement is capped by limestone, sandstone, claystone like this. Now, the whole system is folded. So, due to the folding of the whole system, a geographically positive area occurs here, a geographically negative area occurs here. Okay. Now, once the system is folded, now you see due to this stretching some cracks are developed. Due to development of these cracks, the rocks gets physical or mechanical weathering, and due to removal of the material from these antiforms. Now, you see due to removal of this material from this antiform, here gradually a geographically negative area occurs. So, that means due to removal of this material, once upon a time which was a geologically or geographically positive topography, due to removal of this material, this become geographically negative topography, and once becomes negative topography. So, here this example is the Bani Sagar dam or Bani Sagar reservoir. Now, it is occupied by water body, it is behaving as a reservoir. That means, reservoir means it is a geographical negative topography. But if you go to the geological past here, if you see here, this is the block diagram showing earlier this was the topography was like this, the topography was like this. But due to this removal of this material, now becomes a negative topography, and finally, it is the site for the Bani Sagar reservoir. Similarly, anticlinal valley and synclinal hills are well seen in the Himalayan terrain also. It is a classical example of Himachal Pradesh near to Saketi. If you see here, from the distance you can even see this is the synclinal part, this is the synclinal part, and this synclinal part, it was earlier it was a valley, synclinal part. Now, see here this is synclinal part, this is behaving as a valley, the anticlinal part it is behaving as a ridge, but due to this removal of this material from the anticline, this becomes a valley, and the adjacent ridge becomes a valley, and the valley becomes a ridge. This type of topography they are called matured topography. That means, for a long geological time that has been suffering, these geological agents are continuously working together, and finally, the topographic inversion occurs. This type of topographic inversions mostly they are found in the matured topographic area, which is large for the large geological, for a longer geological time they are exposed to the surface. Another type of weathering by expansion or the removal of the overburden due to expansion from the subsurface is the classical example of salt dome, evaporite. Evaporite, salt, generally they are the indicator of arid climates. Salt dome they occurs in the subsurface, and due to their low density they try to expand. Due to addition of more and more salt, the salt dome try to expand because density is low, the material is being added. So, that has to occupy large space. So, in order to occupy the large space, expansion occurs, and due to expansion it uplifts the region, the overlying material getting uplifted. So, once they uplifted, so they are more prone to weathering, because higher altitudes they are more prone to weathering as compared to our lower altitude counterparts. So, that is why due to formation of evaporite or salt, due to expansion, this overburden. Now, you see earlier this bed it was with the continuation with this one, similarly this bed it is continuation with this one, is not it. So, now once we are uplifting a system from the subsurface, so it becomes an anticlinal form. Okay. So, that is why it is cut off this two beds, now they are separated, one bed they are separated from its other side counterpart. So, that is why what happens, this expansion occurs, and due to expansion erosion occurs. Now, you see salt valley anticline. Salt valley anticline, due to expansion removal of the overburden occurs, and due to removal of the overburden it becomes a valley. So, this is another kind of example of physical weathering by salt dome expansion. Now, the second point is the growth of foreign crystal in the cracks of the rocks. This is another prominent point of physical weathering. What is growth of foreign crystals? Foreign crystal means the crystal or these rocks which are formed outside, that is foreign crystals. So, now that means it has no relation to the rocks which is hosting it. Mostly this in higher latitudes and higher altitudes, water plays a major role in forms of ice for expansion and cracking down of rocks. That is very important to understand here. In high latitudes and high altitudes, suppose we have cracks in the rocks and we fill it with water. So, during the winter or even if it is in higher latitudes, every time the water is converted to ice. So, once water is converted to ice, its volume increases. So, here if you see, water increases 9% specific volume, but the expansion ratio increases in a confined system to the same temperature. Once we convert water to ice, its volume increases 9%. But the same case, if the water is confined within a system, confined within the pore spaces, confined within the cracks, the ratio increases more. So, that is why it will put pressure on both sides of this crack wall, or it will put pressure on the pore spaces. A maximum pressure of 2100 tons per square foot is observed at minus 22 degrees Celsius. That is sufficient to cross the strongest rock. Very important here to understand. Even if the strongest rock, basalt, granite, we create cracks and the crack is filled with water and we allow it to freeze. So, this whatever the ice will be created, that will expand these cracks and its pressure will be 2100 tons per square feet, and that in minus 22 degrees Celsius. That much pressure is sufficient to cross the granites, the basalt, even more strongest rock. So, that means the cracks filled with ice or filled with water converted to ice, that means ice is the foreign crystal for the rock. So, these are very much responsible for this expansion of this rock and a prominent reason for this physical or mechanical weathering. This is other word, it is called frost wedging, because it is a wedge of frost, it is wedge filled with ice. Here how this frigid ice growth occurs and how this volume of this ice occurs and how the thickness of these cracks increases with time is given in this figure. Now, see the formation of ice wedges, there are different stages is given. The first winter, this is the cracks filled with ice, and this is the first summer, the ice is getting it is melting, and finally, this is filled of water. Now, in the second winter again there will be filled of ice. So, there is a boundary between the first ice and the second ice. Similarly, in the second summer, part of the ice is converted to water and part remains as ice, and in hundreds of winter, that means hundreds of years, if it remains there. So, finally, the volume of ice getting increased year per year, and that is why its volume gradually increases. Finally, the cracks are earlier when this crack was formed, the size was this much and after hundreds of years this cracks width is this much. So, not only this much, if you see here earlier the crack this extension is up to here, but now you see due to volume increment now this crack is moving downward also. So, lateral and downward increase of these cracks finally makes the rock fragmented into different small particles. So, this is another example of growth of foreign crystals in the physical weathering. If it is permafrost, now if you see, if you go to these news and research papers, due to this climate change the permafrost regions are mostly affected, like the Alaska in USA and the Siberian, these are the permafrost regions. So, in the permafrost region what happens, the lower part in the soil profile there is totally frigid, they are totally frigid. So, you know soil profiles, there are pore spaces, the pore spaces we have water, they are in frigid condition, and frigid condition that means there is a expanded volume, ice once it is there. So, it is in the expansion form. Now, due to climate change, once the temperature increases 1 degree, 2 degree or so. So, these permafrost region, these ice sheets which in the pore spaces they are melting. Once this pore space was occupied by the ice, it filled with ice under expansion condition. So, now if it is melting that means it is squeezing that 9% specific volume, that is squeezing. Once it is squeezing that means the pore space is increasing, the volume of pore space is more. So, that is why the surface it is subsiding down. So, this is the most severely facing problem in the permafrost region nowadays. So, now you see here in this figure, these are this development of the cracks in the permafrost region due to melting of ice. So, in Alaska, in Siberia, these are the most severely facing problem nowadays. So, this is an example of ice sheet melting and growth of ice sheet in physical or mechanical weathering. So, another example of foreign crystal growth in physical weathering is the pyrite, occurrence of pyrite. Pyrite we know iron sulphide. Okay. So, here you see pyrite generally it is found in shale, limestone if iron and sulphur are there. Now, it is pyrite occurs in reducing environment because oxygen is not there, that is why sulphide FeS2 sulphide it is occurring in a anoxic environment. Now, suppose a cell surface is exposed, to the atmospheric condition or to the water. So, here this iron is easily reacts with the water, the oxygen, so removing the sulphur. So, once it reaction occurs, it is an exothermic reaction. So, here newly formed iron oxide, so that will form iron oxide rather than iron sulphide, sulphur will remove. So, this newly formed iron oxides are lower density and larger volume, So, that means volume expansion occurs. Once volume expansion occurs, that means it will create some cracks, it will stress the rock outward. So, that means cracks or expansion cracks will be developed. Suppose here a pyrite crystal is growing, here a pyrite crystal is growing. So, here it is fracturing the rocks, here this one is also fracturing rocks. So, two fractures, here it is growing this word, this is growing this word. So, this mix together, and two fractures mix means one fragment of the rock comes out. So, this is one type of mechanical or physical weathering. Here what happens, this pyrite oxidation, you will not believe, it will create this type of smokes. So, that is why in many areas in the earth, due to this pyrite oxidation, the hills are called smoking hills. This type of vapors or this type of smokes they occurs. So, these are named as smoking hills. So, smoking hills, that means there will be pyrite oxidation, and this due to pyrite oxidation, this volume expands. Due to expansion of this volume, it creates cracks, and cracks migrate from one place to another and intermix with the another cracks, interact with the another cracks. Finally, rocks are getting fragmented. Now, another region of physical or mechanical weathering is called salt crystallization. So, we know in water there are many salts that are in soluble form. So, due to drying of water or due to this EH-pH changes, the salt has to crystallize. Suppose a rock body which is saturated with water, and this water containing salts, and the salts is removal from this rock body itself, or the salt it is removed from somewhere else, transported through the transported through the water and remains in the pore space. Suppose due to the change of EH-pH condition, salt crystallization takes place within that water body, within that pore spaces. So, once this salt crystallization occurs, it will expand the system. So, once it is expand the system, again cracks are developed there. Here the force of crystallization around the nuclei of precipitating salt is substantial, very important to understand here. The force of crystallization, once the salt crystal takes place, crystallization takes place within pore space. This force of crystallization, it is very much as compared to this strength of the rock is concerned. For example, example is given here, halite crystals, when precipitating over a range of temperature between 0 to 50 degrees Celsius from supersaturated solution, generates crystallization pressure ranging from 54 to 366 megapascal, which is sufficient to crush a rock. So, that means salt crystallization within the pore space of the rock, it is also playing significant role in expanding or in cracking the rock which it is being hosted. Such pressure exceed the strength and almost all rocks, and cracks are developed. Supersaturation is a necessary condition for the growth of salt crystals, but it is easily achieved either by cooling or saturated solution or by evaporation. Suppose we have these playas in that is deserts. So, here the supersaturation of water occurs. Similarly, water is isolated in a basin, small basin or small hole type, small ditches. So, due to evaporation, salt precipitation occurs. Even on the walls, once the bricks are saturated during rainy time, and during summer this water is evaporated. Finally, the salt are precipitated on the brick wall. So, those salt, that precipitated salt, that means this force of crystallization, the force of nucleation, it is very much fast and very high, so that it can create micro level of cracks on the walls of these houses or even the rock surface. So, once the micro cracks are developed, so that means it creates a passage for the other agent, passage to this air, passage to the water into the rock body. So, that means further these rocks getting fragmented due to this type of agents. So, this is another example of mechanical weathering. Dendritic crystals, you might have seen in some walls, some rock fragments, there are dendrites. Here this is example of a dendrite is there. Dendritic crystals or even crusts may be found in caulks along mortar joints and buildings, or in the grain boundaries with permeable of otherwise coherent rocks. Here, due to this salt growth, due to salt crystal growth, due to dendritic growth of salts, the cracks getting expanded. Once it is getting expanded, so that means it is promoting physical weathering. This hydration pressure, hydration and dehydration. Hydration means addition of water, absorbance of water. Water is absorbed by rocks, mostly the clays. Mostly the clays they absorb water and expand themselves. So, this is hydration. Dehydration, that means they release water and getting contracted. So, generally the clays, the muds, due to hydration and dehydration repeatedly, they create cracks, and those cracks, once the hydration dehydration cracks are developed, that means it creates passage to percolate water, to percolate air, to passage of air to the rock body. So, once air, water they passes through, so that means physical, biological and chemical weathering both they are promoted. So, that is why dehydration and hydration reaction, they are also responsible for physical and mechanical weathering. Here it is an example given, the hydration pressure of common salt ranges from 10 megapascal to more than 200 megapascal. Common salt, which by absorbing and by releasing water, this hydration and dehydration pressure is varying from 10 megapascal to 200 megapascal, which is much more than breaking of a rock, or the as per the rock strength is concerned, or compared to the rock strength, this much pressure is much larger to break this rock into fragments. Then taphonomy, it is a special kind of weathering, mostly found near to the shore, and it is the reaction between this water vapor, the salt saturated water vapors, as well as these salts in the rock. So, water vapor and salts in the rocks react together, and finally, this type of honeycomb structures they are formed. Common feature of deserts and semi-arid regions, especially near to coast, or whether salt can precipitate from the dew or fog. Once salt precipitated here on the rock surface, we know the crystallization pressure is high. So, once the salt precipitates on the rock body, so it creates micro cracks, and those micro cracks they are responsible for weathering. Then hemispherical pits are also found. If we have granitic body, we have sandstone body. On the base of this sandstone body, hemispherical pits are generally found, or small caves from the underside of the overlying blocks. In exposed cliff, variety of rocks including granite, sandstone and volcanic rocks. Here we will get the hemispherical pits below that, and that hemispherical pits are nothing due to the salt precipitation, and these salt precipitation, once that occurs, again the same thing, the micro cracks are developed. So, those micro cracks, either it is salt precipitation, or it is by foreign crystal growth, or by pyrite oxidation, or by any means, once the cracks are developed, this creates a passageway for the other agents like air, like water to move inside the rocks, and once the system moves down, these cracks are again expanded with time, and finally, one crack interact with the other cracks, and the rock body are fragmented into different fragments. So, this is the process of physical weathering, and in the next class we will discuss more about physical and chemical and biological weathering. For this today's class, this much is here. Thank you very much. We will meet in the next class.